This new section is entitled Work. Work is force times distance. Now, what is the force? The force is the weight. The force is the weight of an object. It's the weight of an object, and when you multiply it by distance, you get work. But now, what's the weight of an object? The weight of an object is the volume times the density. The Greek letter delta for density. Okay. In other words, if something weighs 20 pounds, if something weighs 20 pounds for a cubic foot. So that's the density. And volume is always in cubic units. Suppose you have 30 cubic feet. Well, each cubic foot weighs 20 pounds. That's what that says in the brackets. 20 pounds per or for every cubic foot. So you have 30 cubic feet. So the first cubic foot is 1 pound. For the second cubic foot, it's 20 pounds. Let's try that again. For the first cubic foot, it weighs a pound. For the next cubic foot, it weighs a pound. For the third cubic foot, it weighs a pound. All the way up to, for the 30th cubic, did I say a pound? For the first cubic foot, it weighs 20 pounds. For the second cubic foot, it weighs 20 pounds. For the third cubic foot, it weighs 20 pounds. All the way up to the third cubic foot, it weighs 20 pounds. In fact, the cubic feet cancel out, and you're going to have 20 pounds 30 times. Well, that's just what that says. 30 times 20. 3 times 2, 6. Don't forget the 2 zeros. This 0 and that 0. It weighs 600 pounds. So it makes sense to multiply the volume by the density. But that's just the weight. Let's not forget to multiply by distance. We use small d. So to find the work, it's the volume times the density times the distance that you move the object. I mean, of course, if you are given a problem like this, the weight is 700 pounds, and 700 pounds, and the distance you want to move it is 5 feet. Well, then the work is the force, which is the weight, times the distance, and you have 3,500. Foot times pound is, or pound times foot, is foot-pound. And if I remember my physics right, and if I'm wrong, I'm sorry, a foot-pound is called a slug. But it's definitely, the work is 3,500 foot-pounds. Oh, I don't know why the W didn't come out. Force is the weight. The weight is 700 pounds. So in this case, you didn't have to break down force to volume times the density. But in the next problem that I'm going to do, you certainly have to do this. Okay. Suppose you have a cylindrical tank, and it's filled with water. And the density of water is known to be 62.4. That's the density of water. Now, you are told that this tank is 12 feet tall. The radius is 8 feet. Now, you want to pump, and it's filled with water. The whole tank, all 12 feet, filled with water. And you want to pump out the water. You want to pump it out from a tube that's 3 feet above the top. That is, you have an additional 3 feet. Like, for example, this water drop, you have to bring it up to the top and then 3 more feet to pump it out. You want to bring it up to the top and then 3 more feet. Why? Because that's where the tube is, where it comes out of. It's just the way it is. The question is, how much work is required to do this? So what you do is, you pick, first let's put some axes in. X-axis, Y-axis. And let's concentrate on this one slab of water. Well, so moving this slab of water up and out, that's only a little bit of work. That's only part of the work. So we'll call it delta W. Delta W. And it's going to equal to the volume times the density times the distance traveled. Now, I'm going to, remember I labeled the y-axis. I'm going to call this height, y. Okay, now the volume is, well, it's a circle. It's pi times the radius, which is r, squared. That's the area of the circle, times the thickness. The thickness is going up and down. It's a change in y. The thickness is a y. Okay, that's just the volume. That's V. This is V. And then I multiply it by density. The density of water, and it's filled with water. The density of water is 62.4. Times the distance. Well, how far do I have to bring it? Well, this whole height, that is from the bottom of the cylinder to where the water comes out, is 12 feet plus 3 feet, or 15 feet. So the question right now is, how long is this distance? That's how long I have to raise it. That's how long I have to lift it. And always, so, along the y-axis, right at the top is 15, and down here it's y. Whenever you want a vertical distance, if you want to know how far it is from 2 to 14, you do top minus bottom. In our case, top is 15, bottom is y. We want to lift it. 15 minus y feet. But I just don't want to do it for the one slab that I have denoted. I want to do it for this slab of water, and this slab of water, and this slab of water, and every slab of water in between. That is, I am going to integrate. And these slabs, well, the lower slab is right at the bottom where y is 0 that I have to lift up. And the highest slab that I have to lift up is at the top, which is 12. There is no slab that's 15. From 12 to 15, there's no water. The cylinder only goes up to 12. Okay, so this is the integral that I need to do, or, this is the integral I need to solve, work out, and we do so when we're done. Okay, let's factor out the constants. This is 64 times 62.4 times pi. And what survived is I brought out the pi, the 64, the 8 squared, and the 62.4. What survived is 15 minus y times dy from 0 to 12. Okay. Turns out the product of those two numbers is 3993.6 times pi. The integral of 15 dy is 15y minus integral of y, y squared over 2. And we go from 0 to 12. So I have 3993.6 pi, and you plug 12 in for y. 15 times 12, if I'm not mistaken, is 180 minus 12 squared, which is 144 over 2. 72. So this piece is 108. And when you multiply 3993.6 by 108, you get 431,008. See the that's me 3 point pi. That's the amount of work needed to move or to pump all that water out of the tank. And force what of this? Well, it's it up 15 minus work times distance. And I had to keep doing this. When you keep adding things up and it's continuous, those slabs are right next to one another. There's no gap between them. That's integration. That is integration. Let us try another one. Suppose you have a right circular cone, and you were told that the radius, the diameter, is 8 feet. And you were also told that it is 6 feet high. I actually had to work that. I don't normally do that, but that's because the numbers work out so unfriendly. And once again, it's filled with water, and this time, you just want to pump the water out the top. Okay, you don't have to go above the top. You don't have to go a foot above the top or an inch above the top. So regardless of that comment, I would still put some coordinates down, the x and the y axis. Okay. And we know that the work is equal to the integral of the volume times the density times the distance that the water is being moved. So let's look at a particular slab. Let's look at that one. Oh, what's the volume? Well, the volume, it's a circle. It's pi times r squared, and it has their dy. That's the change in that volume. But what's r? What's r? And this particular height, we'll call it y. Y equals 0 down there. We call it y. Now somehow we need to come up with a ratio. Now for that height y, that's the radius. That's the radius. Okay, and the height is y. Now the thing, so we have a similar triangle. Don't think of this as a circle. Think of these as straight lines. We have similar triangles. We have this big triangle where the base is 8 and the height is 6. So we have 8 is to 6 as, and now we have this smaller triangle down here. Let's draw it. The height is y, and, okay, this is 2r. So their diameter, I put the diameter on the top, and the smaller one is 2r, and in the bottom, I put the height. This reduces to 4 over 3. So I want to solve this for r. We have that 4 over 3 is 2r over y. Just bring this y up there, you get 4y. Bring just the 2 down there, you get 6. And leave the r where it is. R is 4y over 6. But this can be reduced to 2 over 3. That is, r is 2y over 3. Okay, well that's helpful. So the volume is pi times 2y over 3. That's r squared dy. That is, it's pi times 4y squared over 9 dy. That's the volume. Okay? The 4 pi over 9 I can pull in front. 4 pi over 9. Now let me erase my side work. Whenever you have these cone problems, you should do these ratios. What you're doing, max-min problems, related rate problems, or these work type problems. Y squared dy. That's the volume. Density is 62.4. It being a constant, I pull it out in front. Now, what's the distance we brought this? Well, I'm saying we're at a height of y, and we want to bring it up here, which is a height of 6. It's 6 minus y. That's the distance. Okay, I'm not clear why this didn't come out. Okay, so let's just do it again, and that will be it. So the distance traveled is 6 minus y. The volume I have down here in the bottom, its constant is 4 pi over 9 times the integral of y squared dy times the density, which is 62.4, times the distance, which is in terms of y, it's 6 minus y. Okay, so we have 4 pi times 62.4 over 9 times integral of 6y squared minus y cubed all times dy. Now what's y going from? Well, the smallest slab starts at 0, and the highest one is, just before 6. Goes from 0 to 6. So we get this number, whatever it is. Let's see if I wrote it down. No, I didn't. 4 pi times 62.4 over 9. This integral is 2y cubed, plus the derivative of 2y cubed is 6y squared, minus y to the 4 over 4. And we are going to evaluate this from 0 to 6. Okay, so we get this silly constant in front. And since I don't use calculators, I always try to do things more easily. This is 2 times 6 cubed. Now, this, when you plug in 6, you get 6 to the 4th, which is 6 times 6 cubed. So you get 6 over 4, 3 over 2, times 6 cubed. I mean, just like if this were x. If you have 2x and you take away 3 over 2x's, you have 2x's and you take away 1 1/2 x's, you have half x. This time you have half of 6 cubed. X is simply 6 cubed. I'm not going to calculate 6 cubed times 2 and 6 cubed times 3 over 2. I'm going to factor out 6 cubed. And if you'd rather me write it down that way, fine. 4 pi times 62.4 over 9. I factor out 6 cubed. There it is, and what's left over is 2 minus 3 over 2. But that's just a half. So the final answer is whatever 4 pi times 62.4 is over, times 6 cubed times 1, don't bother, divided by 9 times 2, which is 18. You can kill off one of the 6's on top with one of the 6's in the bottom. Remember, 18 is 6 times 3, so the 3 stays. And if you actually work this out, you should get 2995.2 pi. 3 goes into 62.4. Number of times, let's see, 20.8 times. So it's 4 times 20.8 times 2. 4 times 2 is 8 times 20.8 times pi. Okay, so that finishes that problem. Let us try one more. Suppose we have a sphere, and it's only half full with some kind of oil. This time we'll have a different density. And we want to pump it out from the very, very top point. Even if there's a sphere, there's only one top point. So there's our sphere. It's cut in half. This is filled with oil. Halfway full. The density of the oil is 50 pounds per, cubic foot. That's the density of the oil. Now, we want to pump the bottom out the top. Want to pump it out at that top. And like always, work is going to be the integral of the volume times the density times the distance. This is force times distance. That's work. There's a lot of work done, so we have to add it up, hence integral. All right. So let me erase this. But remember, it's only halfway full. Now, let's put some kind of a coordinate system in. Call this the x-axis. And as long as it's perpendicular, it's okay. In theory, you can call these the axes. As long as they're perpendicular. This is y, this is x. Okay, it's up to you how you put it. Now, why am I even mentioning it now? Because it looks like the regular coordinate system. Let me erase this and I'll make it slightly different. Down here is a positive y. Down there is a positive y. And the radius is 8 feet. Okay. The radius is 8 feet. So the equation of the circle in front of us is x squared plus y squared is equal to 8 squared. Now, why am I doing this? The reason is here is my arbitrary slab right here. It's at a height of y. Remember, here's y0. And this time, that's just y. I want to know the equation of that. Well, I know it's x squared plus y squared equals 2. What's r? What's r? Well, it's an x value. Solve this equation in front of us for x. Bring this over to the other side. And x squared is 64 minus y squared. And I'll get the positive solution. We know x is plus or minus the square root of 64 minus y squared. I'll just keep the positive. That's my r. The volume of that slab, the volume of this slab is the circle, pi times r squared. And when you square this, you just get 64 minus y squared times the thickness, which is dy. That's the volume. This is pi times 64 minus y squared times dy times the density, which is 50. Now, what's the distance? How far do I have to bring this slab? Well, I have, remember, this height is 8. I need to bring it that distance. Okay, so let's be careful. First I bring it up y, and then I bring it up 8 more. I have to bring it up y plus 8. I have to bring it up y, to bring it up y plus 8. Now, if you want to be exact, this height here is negative 8. And since I reversed where the positive y is and the negative y, instead of doing top minus bottom, I'll do bottom, which is y, minus the top, which is negative 8. And here, I get y plus 8. Okay, that's the integral that we need to solve. And what does y go from? Well, remember, the y down here is 8. So, let's see. This slab down here starts at 8. And then I do this slab above it, and then that slab above it. And then eventually I do the one right at 0. Goes from 8 to 0. I don't think I have that backwards. If I get a negative answer, then I should have gone 0 to 8. Well, let's think about this. Let's think about this. The first thing you have to do is pump up that one, the one at 0. I claim the bottom limit should be 0. And then you have to pump up the one that's at 1, and then the one that's at 3, and of course everyone in between. And then lastly, the one at 8. So sorry, it goes from 0 to 8. Goes from 0 to 8. Sorry about that. Okay. Come on. Got it. Well, the pi times 50 in front. 50 pi. And then we distribute this out. You get 64y plus 512 minus y cubed minus 8y squared, all times dy. So this is 50 pi. Integral of this is 32y squared, or 64y squared over 2. Is 64 over 2 is 32. Plus the integral of that is 512y minus y to the 4 over 4 minus 8y cubed over 3. And we evaluate from 0 to 8. Evaluate from 0 to 8. Now I claim that 8 cubed is all over the place. Remember, this is 4 times 8. When you plug in 8 squared, 8 times 8 squared is 8 cubed. You have 4 times 8 cubed. Plus, 512 is 8 cubed times 8. That is, you have 8 times 8 cubed. Minus 8 to the 4 is 8 times 8 cubed. Well, 8 over 4 is 2. You have 2 times 8 cubed. Minus 8 over 3 times 8 cubed. And when you plug in 0, you get 0. So basically, you can actually factor out the 8 cubed. You have 4 plus 8 is 12. Minus 2 is 10. Minus 8, well, think of 10 as 30/3. So basically, it's 50 times pi times 8 cubed, which is 512. And when you do this math, you get 22 over 3. 22 over 3. And there's the answer. Multiply these out. Save the pi. That is, multiply 50 by 512 times 22 divided. And let's see, when you do the multiplication, you should get 56,000 or 563,200. When you multiply 50 by 512 times 22, minus some silly error on my part, you get 563,200 times pi, and do not forget to divide it by 3. And there's your exact answer. The next type of problems we're going to do for this work section is Hooke's law. And talked about spring constants. How much force is required to move a spring a certain distance? Now, the first thing I want to talk about is, you've all done this. You stretch a spring long enough so it's no longer a spring. Okay? You cannot do that with these type of problems. In other words, we are going to assume that when we move the spring 3 feet or 4 inches or whatever distance that we are saying, that the spring is still a spring. Okay, it's still a spring. Now, if you think about it, if you take a little spring from a pen versus this really big, heavy-duty spring, and I'm trying my best to make it the same size, it's going to take a lot of force to move this spring, so it's only, you moved it down that amount. You moved it down that amount. To move this spring down that amount, put a penny on it. It'll move down. But this big spring is going to take more of a force to move down. Hence the terminology, the spring constant. Different springs have a different constant. The heavier the spring, the harder it is to squeeze it or push it down, that is, the bigger the spring constant. The easier it is, the smaller the spring constant. And this is all under the heading of Hooke's law. And Hooke's law says that the force to move a spring x units is k times x. Or just kx. F equals kx. Now the work, like always, is force times distance. That is, it's kx times the distance. But the movement of the spring is continuous. First you move it 1/4 of an inch, and then 1/2 inch, and 3/4. You can't skip, if you compress the spring, 2 inches, that is, the spring went down 2 inches. When you're actually pushing it down, you had to you had to displace it every single amount between 0 and 2 inches. At some point, of course, it's going to be for a split second, but at some point, the spring went down 1/4 of an inch. And then it went down 4/16, went down 5/16 of an inch. And then it went down a little more, and then a little more. And eventually, it went down to 2 inches. It was continuous. That is why we can say integrate. It's the force required to move it from 0 to 0.1 inch, plus from 0.1 inch to 0.2 inch, plus from 0.2 to 0.3 inches, all the way up to 2 inches. And I really shouldn't even be letting, dx. I shouldn't be letting the dx even be that much. Remember, the dx's are infinitely small. I was letting dx be 0.1. Okay, nonetheless, there is your formula. That's the work required to move the spring from its natural position from C to D. And now, before you can do this integration, you have to know what K is. You have to know what K is. So you have to be given some information. This reminds me of problems in the past where you had directly proportional, inversely proportional. You've seen this, I guess, in pre-calc or one of your algebra classes. You are told, for example, that a force of 750 pounds compresses a spring from its natural position, compresses a spring from its natural position, and the natural position is how it behaves or how it looks like when you just don't put any force on it. You may put a force on a spring, and let me do it this way. Maybe it looks like that. But you take the force away, and it's nice and calm looking. It looks like that. There's no compression going on. Just let the spring go, and however it goes, whatever position it looks that it's in, that's the natural position. Okay, a force of 750 pounds compresses the spring from its natural, it compresses a spring, say, 3 inches from its natural position. Okay, and the question is, find the work, find W, in compressing the spring an additional 3 inches. Find work in compressing the spring and additional 3 inches. Okay. So basically, in our formula in this box here, which I'm erasing for some reason, what are C and D? Where is the spring going? Now, just to talk about from its natural position. How much work is required for moving it 3 inches from its natural position to an additional 3 inches? It is from 3 to 6. So we can integrate this and we'll be done if only we knew where K is. We know Hooke's law says that F is K times X. The force is 750 pounds. The force is 750. And it equals the K times some distance. Well, the force is 750 pounds compresses the spring 3 inches. K times 3. 750. Well, I know 25 times 3 is 75. So just add a 0. K is 250. K is 250. This implies K is 250. So now I can do this integral. I want to know what's the work required to move it from 3 inches from its natural position to 3 more inches. That is 6 inches. So the work is the integral from 3 to 6 of K x dx. The 250 can come in front. The integral of x dx is x squared over 2. This is 125. So it's 125 times x squared, evaluated from 3 to 6. Now, I'm going to erase the bottom left here for my extra space, for additional space. It's 125 times, I'm going to factor out the 125, times, you plug in 6 squared minus, now you plug in 3. 3 squared. Well, 6 squared, 36. Minus 3 squared is 9. That's 27. It's 125 times 27. Well, 27 times 100, 2700. Plus 27 times 25. The value of, that's the same as 25 times 27. The value of 27 quarters, you should know that. The value of 27 quarters is going to be 675. And if you happen to add these two numbers, you get 3375. That's the amount of work required to move the spring from 3 inches beyond it or compress it between 3 inches to 6 inches from its natural position. So we're not counting the work to get to 3 inches. We're not going to count the work required to move it the original 3 inches. In fact, that was given to us. It was 60 pounds. That was actually given to us. No, 750 pounds. Sorry, 750 pounds. All right, let's try another one. A force of 60 pounds stretches. Doesn't matter whether we compress or stretch. Our force of 60 pounds stretches a spring 1 foot. So this is going to help us find K. How much work is done in stretching the spring to a length of 6 inches? How much work is done to stretch the spring 6 inches? Now, basically, you have a spring. And if you pull it up, eventually, it's just not going to be a spring anymore. For these problems, we assume that whatever we're doing, it maintains the property of a spring. It doesn't just become a wire. It's still a spring. Okay? So, we know that F is equal to Kx. The force of 60 pounds, F is 60, stretches a spring 1 foot. Well, we all know that 60 times 1 is 60. The spring constant is 60. As long as we're in feet, okay? As long as we're in feet. I mean, if we're in inches, 1 foot is 12 inches. And 5 times 12 is 60. So now the spring constant is 5. But we'll stay in feet, and the spring constant is 60. So F is equal to 60x. Okay, F is equal to 60x. Now, what is the work done to move the spring 6 inches? Now, something I said is very important. 60 is the correct K, as long as we do our problem in feet. So, just remember that, where are we? Just remember that 6 inches is half a foot. So we want to move or stretch the spring from 0 feet to a half a foot. And we do F 60x dx. And we get 60x squared over 2, from 0 to a half. Well, that's 30. We get 30 times x squared from 0 to a half. Well, when you plug in a half and you square it, you get a quarter. And when you plug the 0 in, you get 0. A quarter minus 0 is still a quarter. A quarter times 30 is 7.5. 2 goes in here 15 times. 2 goes in the bottom 2 times. 15 times 1 is 15 over 2. 15 over 2 is 7.5. That's how many pounds is required to move the spring from its natural position 6 inches. Okay, now for the record, it doesn't matter whether you compress it or stretch it. You're going to get the same exact answer. This completes the section on work. Thank you.